Thank you so much, Anmol, for giving this presentation.
Anytime. Thank you, Arturo, for asking me to try this. It's amazing. All right. Greetings to all of you. It's good evening. I hope you all are still there and hope everyone's doing good. So I am a PhD candidate. My name is Anmol. I'm a PhD candidate at Propulsion and Nanotechnology Laboratory at George Washington University, working under the guidance of Dr. Michael Kaider. Some of you may be familiar with him, his name. And I am working specifically in the field of propulsion. In our laboratory, we work in the field of nanotechnology, cancer research using plasma medicine, cancer research, and propulsion. So I am working in the propulsion side. The topic of my project or my thesis is analysis of ionization in air-breathing plasma thruster. But our ultimate goal is to design an air-breathing plasma thruster and test it. But just for this research, I built a model, and I'm analyzing the results of ionization that is happening inside like a global model. So the link to our website is shown below. So we're going to talk about the research at MPNL, micropropulsion nanotechnology, followed by specifically targeting towards, which will be like the entire presentation would be targeted towards air-breathing plasma thrusters. We're going to talk about the objectives of this presentation. So that's very important. Like, why do we do this research? What's the importance? Then we will study the ionization reactions. So basically, I built a database of 167 chemical reactions corresponding to air ionization, and the results related to that, why they are important and why we have to study that. So we will basically be talking about it. And then finally, all these results are based on a global model. So a global model of an air-breathing plasma thruster. You must be asking me what that is, like what's an air-breathing plasma thruster, which I will also explain, but it's a type of an ion thruster. And the performance calculations, as we know, like is talking about drag, thrust, power, etc. And then the future work, which will be involved in the for in-depth analysis. Let's talk about plasma medicine research. And just to let you guys know, my friend, he is working primarily on this research in our laboratory. And if you guys have any questions, he's also in the meeting. And feel free to ask any biology related questions as well. And because my background is not biology, my background is aerospace, so I can like talk about electronics and like some underlying mechanism regarding our research in plasma medicine as well. But if you want to know like in-depth analysis and like biological questions if you have and stuff like that, so you can definitely I can pass along your questions to him and he can answer those. All right, so here you see 3 images. Let me put on the pointer. So the first image A shows a copper ring. So in our laboratory, we have built this device called cold atmospheric plasma jet device. What it does, it's so like just talking about the structure. So it's a tube and you have a cathode and an anode. We inject helium at some flow rate, let's say 10 milligrams per second. And then we ionize that helium in a high alternating current electric field. After ionizing the helium, and the tube is exposed to the air, so it's not in vacuum or it's not like forming inside very low pressure. It's like atmospheric pressure. That's why the name suggests as cold atmospheric plasma. Now you must be thinking about why is it cold? So it is cold because if you put your hand in front of that jet, like it has the same temperature as your body temperature. So it's like it's the room kind of like a little bit cooler than room temperature. And it's not going to burn your hand or something, like it's like low temperature plasmas. And in our laboratory, we primarily focus on low temperature plasmas. Here, what we have done is the jet that is coming out, we are using this jet to treat different types of cancers. And there are multiple applications for this jet that we have used the jet for. And specifically in this image, as you see, we have a copper electrode ring. The jet, so we see plasma, in a form of image, but visually, but inside that plasma, there are millions and billions of chemical reactions happening. My presentation, my research will primarily initially be focusing towards chemical reactions. So speaking of chemical reactions, and also which leads to your optical emissions. So here with the external electrode ring, you can control that chemistry. You can control the evolution of electron density, which thereby can also control the evolution, or like you can basically if you like bias it to a very low voltage, you can increase the densities of reactive nitrogen and oxygen species that are created, and which also affects your optical emission spectrum. The B image that you see, so our laboratory has proposed this idea in which we have the plasma jet, and we are basically, so we have a water solution, and we are activating that water solution using the cold atmospheric plasma jet, filling all the required reactive oxygen and nitrogen species, and then you can just drink the water. So the best thing out of this is that you don't need to inject that plasma into the skin, or you don't need any invasive methods. It's a non-invasive method that has been proposed. And this, so if you go to our research website, you can find out studies related to that as well that we have published. Now comes the most important part, the C part. Here, it is primarily targeted towards brain cancer. So you have the mice over here. And so what we do is we inject the cancer cells into the mice. We wait for a few days. In our case, sometimes maybe 7 days. So the baseline that you see here is basically when the cancer has started to develop. And over the period of 48 hours, you can see the aggressiveness of cancer increases. So you see the redness is increasing. Even the blue part is also the cancer, but the aggressiveness is less. Now the cancer has been developed. So how do we treat it? So we start treating it using a device invented in a laboratory called cold atmospheric plasma jet device, which is which is basically a very small needle, which is injected into the brain, and it starts to reduce the glioblastoma tumors. So as you see in the bottom here, when we start to treat it, the aggressiveness starts to reduce. And the treatment usually is, if you ask about like how long the treatment usually are, like my friend, like he has been doing this research, and it's usually around 15 to 20 seconds for 4 or 5 times. And you can see the aggressiveness of the cancer is reducing. Just to provide a summary of remaining some of the extra work that we have done here, I would like to add another thing to the previous slide is, so my friend who's here in the presentation, so he also came up with this idea that now we have injected, a needle into the brain. So you are basically injecting into the skull. But he also came up with the idea that, and he found out through his research that the jet actually you don't need to inject it in the skull because it can penetrate the bone. So so if you want to go into the medical terms of like, well, what's the bone density and like what bone it is made up of and stuff like that, you can definitely ask him. But he tried to treat the same mice without injecting the needle and just exposing the skull to the jet. And he also like did the test by keeping a bone between cancer cells and the jet, and he found out that we can still treat it. So that's a great thing that we don't need to it's still a non-invasive method. Coming to summary of plasma. So over here, if you see, this is what a plasma bullet looks like. So you can see over here, this is the exit of the plasma jet, and a bullet comes out. So the redness means like you have very high electron density in that region. So this plasma bullet forms is because the plasma this is a streamer propagation. So it's like a streamer propagation. Your helium is continuously being supplied. It's a form of stream. And the electrons are surrounding the exit of the tube because of ionization of air in such a high electric field. They start moving up towards the helium and helium ions. And both of them starts to mix, forming a small kind of bullet or a bubble of quasi-neutral plasma, which basically, as it is propagating, slowly down. So it propagates outside of the jet. To our human eyes, we cannot see it, but we use fast imaging to see it in the nanoscale. So here we have the results plotted basically for seeing the jet bubble. Then comes the in vitro and in vivo application. So in vitro basically involves treating using the jet to treat the cancer cells without with just the cells outside in maintaining it at room temperature. In terms of in vivo, here they had injected the ovarian cancer And over the period of 25 days, the ovarian cancer literally disappeared with the jet treatment every day. Then over here, you can see the solid tumor on a brain of mice, and the black area shows the aggressiveness of the tumor. So with the treatment and interaction with the helium cold atmospheric plasma, or I can say the CAP, let me just say CAP instead of the entire term. So it started to reduce it, and the aggressiveness is reducing. It starts to, you can see the gray areas. Those are the areas which have healed. What is the underlying mechanism behind it? Like, why do these cancer cells die, and why do the normal cells do not die? So that's because in general, like cells, they have a threshold for their reactive oxygen species. With increase, so from the jet, the cold atmospheric plasma jet that we are supplying extra reaction oxygen species, which basically increases, goes beyond the threshold of the existing like cells reaction oxygen species threshold. And especially in cancer cells, we have higher ROS, reactant oxygen species, which basically, because due to increase of ROS, it dies, whereas the normal cells have the tendency to come back to the threshold. So it kind of it goes up, but the threshold, it can come back to its fall back to its threshold value. So normal cells don't die and cancer cells die. So this is the underlying mechanism for our jet. This was all the summary about the medical side. Let's talk about propulsion. So this is where like my research starts. So these are some of the 3 CubeSats that we developed for NASA in the past. So we have the PhoneSat mission. We have developed the microcathode thrusters for these CubeSats. So you can see over here, this is a microcathode thruster, which is based on the vacuum arc technology or vacuum arc thruster technology that we have used to build thrusters. So individually, we can produce thrust, but through these experiments, we kind of achieved multiple thrusters in one unit, thereby reducing the weight of the payload, reducing the overall power, and then also trying to fly 2 CubeSats in the same formation. And there were different mission statements regarding it. So you can visit these websites and take a look. And our ultimate aim always has been to increase the thrust to power ratio for the microcathode thrusters. Some of the additional work in the field of propulsion is like we always, like I just said, like we aim to have higher thrust to power ratios. Then we also aim to have multiple microcathode thrusters to operate together, like we have in the previous slides. Then there's another kind of thruster we worked on was linear drive microcathode thruster, in which what happens is, so the cathode material, so it's a solid propellant thruster. So it's a solid propellant. It doesn't require any gas, and it doesn't even require a neutralizer. So what it produces is basically, it's a pulsed plasma, and it produces spark. That spark is mixed off that spark is a plasma itself, like it's a mixture of ions and the electrons, and ions of like the material, the cathode material we are using. So it's like a cigarette. So when someone smokes a cigarette, the cigarette starts to reduce. The same thing happens with the microcathode thruster, the front part, which is like the cathode, it starts to reduce, and then you need to push the cathode forward to keep utilizing it. So there is a maximum number of pulses you can get out of it. So linear drive was sensing through a capacitive circuit, sensing the reduction, and then it moves it forward. And MPD thruster, magnetoplasma dynamic thruster, we are working on this. One of my friends is working on this using the vacuum arc thruster. And my primary goal is to work on air breathing plasma thrusters. Now comes the main thing, like what is air breathing plasma thrusters? So in general, the plasma thrusters, they use gas like xenon. Let's talk about like Hall thrusters. You have xenon, let's say, noble gas, you operate in vacuum. So now this field, which is kind of like new field and still like in a very like a very baby phase. So ABPT is air breathing plasma thruster. So what we are doing is, as we know, air breathing. So we hear air breathing in all in other places such as jet engines or like turbofan engines or like commercial plane engines or fighter jet engines, etc. Here, what we are doing is, instead of flying in the vacuum, we're flying at a much lower altitude. Much lower altitude means very low Earth orbits. That's around 80 to 250 kilometer altitude. In that altitude region, we don't have vacuum, we have some residual atmospheric air. So we can use, so if we use our satellite, if we use this engine in that altitude, the best thing is what we are doing. We are utilizing that air as a propellant, and which means we don't need any external storage tank. And the engine will keep going forever. Like, obviously it depends on the materials, but you're using the incoming air as a propellant and accelerating the plasma in order to generate thrust. Some of the thrust levels are mentioned here, like 90 million to 90 Newton, to cancel out the drag in those atmospheric levels. And obviously, as we come down towards like that level, as we go to a much lower altitude, the drag significantly exponentially increases. So there's like a very short altitude gap in which we can fly this. And obviously like lower launch cost and etc. But the most important thing is it's a potential solution for space debris. So this is like a very good selling point. If I want to try to sell this idea to NASA, is like, it's a great, it's a great idea to for a solution for space debris. Why? Because you're flying at a much lower altitude. If your satellite goes out of control, it's just going to burn up on re-entry. So you're not creating any unnecessary space debris. So it's because of the decay in the altitude, it's going to burn up. So it's a potential solution, and you are effectively utilizing the space resources. These are some of the designs. I'm not going to go like deep into these designs because of time constraint.
I'm sorry. I got a little bit lost right there. So can you repeat that argument that using this air thrusters, you could prevent the debris or deal with space debris? Can you say that again? Sorry about that.
So with these air thrusters, as they're at much lower altitude, we have higher drag in that altitude, which means if we don't keep so we can decay our satellite back into the orbit. Whereas the other space debris, the problem we have is one, obviously the problem is collecting those space debris. Other problem is we cannot the problem is decaying into the Earth's atmosphere because they're traveling at a very high orbital velocity. Whereas with air breathing plasma
thrusters, the argument is that the satellites would have sort of like a backup air thrusters that if they were to fall into the lower orbit, you could use them to bring them back up. Is that the argument?
No. So basically, ABPT will be at much lower altitude as compared to generally satellites fly at. So satellites fly at way higher altitude. ABPT is still flying at way lower orbit, where if let's say the engine has some problems, or the spacecraft runs out of fuel, runs out of something, let's say it has a problem, it'll re-enter into Earth's atmosphere and burn up on re-entry. So that way, or if there's a collision also, it's going to re-enter and burn up instead of orbiting at hundreds and thousands of hundreds of kilometers of speed. So that's I
got it.
Yeah.
Sorry about that. Yes, I'll let you continue. I understand completely. All right.
Sorry. So yeah, some of the designs, the first one over here you see is a potential design, Citels, the Citels a company in Italy. People in Europe are extensively working on this in this field. So they have a collimator which collects the incoming air. So as we go to much higher altitude, 200 kilometers or something, the air density is so low and the mean free path between the molecules is very high. So what they're doing is they are compressing the air, collecting all the molecules, they're compressing it, and then they have a general Hall thruster to ionize that air and produce thrust. Similarly, we have Hall thrusters designed by Adams research group, which has a radio frequency plasma thruster with combination of helicon Hall thruster. Then we have Fujita's model, in which they have basically analyzed the air inlet for air breathing electric engine. Then we have Professor Kaider's Kaider's research, in which he has proposed a Hall thruster which could fly in the altitude of 80 to 90 kilometers, and build a model based on that. And finally, we have an inductive plasma thruster using RF power to ionize air by Romano's research group. The problem with collimator designs is till now, we're not able to still achieve thrust equal to or more than drag. So the drag is still high. The thrust achieved was 6 million Newton, whereas drag is around 20 something million Newton. So they were not achieving that. So that's why it's not, so it's still a problem. The collimator designs are a problem. Now the problems, the most important part of the presentation, I would say, is we should focus on these. Why we have problems in ABPT. So one thing is we have an external cathode neutralizer. necessarily not a problem, but it requires a separate circuitry, makes the system complex, and then it adds weight to the system. And definitely, if you have higher weight, like you have higher decay in the orbit, and then you need higher thrust to counter it. Then you have corrosion due to atomic oxygen. So in those altitudes, you have very high atomic oxygen, even like comparable with the nitrogen. So that's another problem. Then drag induced by collimator designs. The power requirements will be very high, and the debris. So we already talked about debris. Regarding all the other things, our research is kind of providing solution to that. For the first problem, we provide a solution. And the solution is we are completely going to eliminate the neutralizer, and we are going to achieve self-neutralization in the engine itself by our new concept, by modifying a Hall thruster design. Corrosion, we are reducing corrosion by by preventing the negative oxygen ions forming in the engine to hit the walls and neutralize and causing corrosion. We are extracting those ions, so we are also reducing corrosion that way. And drag, so we are not having any collimator. Whatever air is coming in, we are ionizing it. The only thing is we have a long engine channel. Objectives. The objectives of the study is we will first study, explore, and study the ionization inside ABPT using simulation, explore the idea of self-neutralization, and then perform calculations related to performance for that model. Here we can see this is the most important part. So this is the model we have proposed. It's a it's very much like a conventional Hall thruster. The only difference is like we have one electrode in the beginning and one electrode at the exit. The ring electrodes, basically. We have an open air inlet, and we have two electron sources, one at the top, one at the bottom, which is ionizing the incoming airflow. So the electron temperature is maintained uniformly across the entire ionization zone. And then we have radial magnetic field in order to confine electrons within the, like having a low, like confining them, keeping them magnetized and keeping ions non-magnetized. So what we're doing here is, through our simulations, we observed that we are forming positive and negative ions. So we are trying to extract those positive and negative ions out of this engine in such a way, based on like the time of extraction, in such a way that what we get at the exit, the charge densities we get at the exit will cancel out in order to produce a neutral plume. So let's say if I want to extract the negative charge, so I keep the exit electrode as positive and the entry electrode as a negative biased voltage. And then if I want to extract positive charge, I flip the polarity, and you can do the flipping of polarities using inverter circuits or half-bridge circuits. So this is a major idea. Another thing to add to this would be is that electron source, we are not just providing a constant energy all the time. As we know, negative ions are predominantly also formed at low energies. So what we are doing is, we are, while we are extracting the negative ions, we are also keeping the electron source energy low, like TE1. And then for higher energies, when we are extracting positive ions, we are keeping the energy high. So we are basically, it's kind of like a pulse, not exactly like a pulse. So we are designing this. So our aim is to design this operation time, like to find out T1 and T2 such that when we extract, so these are extraction times, tau1 and tau2 are extraction times, extraction of ions time. So tau1 is for negative ions, tau2 is for positive ions. We design this time ratio time in such a way that when we extract them, outside we will have a neutral plume. So this is how we are achieving neutralization. The equations that are used, quickly go over it. So the most important thing is chemical kinetics equation. This is used to solve the ionization model. Then rest of the equations, charge density, thrust, drag, average power, ion current are used for calculations, performance calculations. Let's talk about the results for 80 to 110 kilometer altitude. Our primary focus was in that. Our simulation time was 0.125 milliseconds. The way we decided the time is based on the orbital velocity. So for ABPT in that altitude, the orbital velocity is 8 kilometers per second. And keeping the engine length maximum as 1 meter, we can find out using the speed is equal to distance by time. We can find out the time of simulation as 0.125 milliseconds. So here in this presentation, I have just shown results of 80 to 90 kilometer. I have not shown 100 and 110 kilometer because as we go high in the higher altitudes, we need larger engine length in order to reach like peak ion density. So That's why like we have not shown 100 and 110 kilometer altitude and or higher length, as well as like, which means like higher and higher simulation time. So these are the results for 80-kilometer altitude. I know there are many graphs in this, but I would primarily focus on some of the key points: 1, 2, 3, 4, 5, 6 here. The first point, if you see over here, corresponds to why do we have a higher O2 plus ion density. So just to tell you what these graphs are, these are the plots of ion densities variation with respect to the simulation time at different mean electron energies for 80-kilometer altitude. So we'll focus majorly on why on these main points instead of like the entire thing because of time constraints. So like the first point, why we have higher O2 plus ion density. Then for 5 EV case, why do we have electron density increasing, whereas earlier it was not? Then for 4, 5, 6 case, which says that why do we have, what kind of plasma do we have in the end after like complete ionization? And here by this point, we know that our plasma, like we have high, like full ionization. So we have reached the peak densities. And then another point is, why do we have, and you can observe we have higher positive ions as compared to the negative ions. And then why do we have a decrease in the curve after increasing? So these are the points that will be addressed. In these two graphs, similar thing is done. Density versus time, simulation time is plotted. But here we are focusing on the neutral densities instead of ions. So the neutral densities have to increase and decrease for like the atomic species like nitrogen and oxygen, whereas for molecules, it will reduce. So because if for nitrogen, oxygen, it was increasing because the N2 and O2, because of chemical reactions, is dissociated into atomic nitrogen and oxygen, and that's why. So the 7th point also we will talk about. So top key points. So we saw O2 plus was increasing. And another thing that was happening was we would see N plus and N2 plus reducing. And the reason for that is the chemical. So I created like an algorithm for plotting a contour plot of 167 chemical reactions. And from that contour plot, you can find out what reaction is the main culprit for decreasing the decrease of the density. So based on that, like I found out like these two reactions, N2 plus plus O2 gives O2 plus plus N2. Here you see if you balance the equation, you see N2 plus is reducing, like the formation rate is reducing, where the formation, like the density is reducing, whereas O2 plus is forming. There is a shift of charge from one species to another. And the similar thing is happening for the atomic nitrogen. So that's the reason why we have higher O2 plus. Then due to detachment of the ions, we have like higher, and with increase in the mean electron temperature, we have higher ionization, because ionization rate is a function of mean electron temperature. And then as a mean electron temperature increases, we see like a bump in electron densities. Similarly, the next point, which is why do we have higher positive charge as compared to negative negative ions? That is because of the charge balance. So the total negative, based on our simulation, the total positive charge density should be equal to total negative charge density, which is of negative ions, plus the electron density. So that's the reason we have high positive charge density. And why did we have a fall in the graph? That was because like it is indicating a recombination. And in the entire plots, we observed 3 main things, which is ionization, attachment reaction causing formation of negative ions, and the recombination due to which the graph started to fall. And finally, the plasma consisted of electrons, N plus species, and O plus species. And for the neutral densities, one thing you can observe here is, if you look at the ion species, let's say 10 EV, around this time they reach the peaks. Similarly, at the same time around, like the neutral densities will reach the peaks. So that was one key observation. Let's talk about 90 kilometers altitude simulation. Let's talk about 90 kilometer altitude simulation similarly. So the main points are 2, 3, 4, 5. I omitted the first point because that first point is related to something else. So 2, 3, and 4, 5. Here also we've done the same thing. We have tried for different energies. So regarding point number 2 and 3, you can see we have higher O2 plus and O2 minus density at 1,3 EV graph and 5 EV graph. We see like higher negative ion and positive ion density here. The reason for that we will talk. Then we see like from 10 EV to 20 EV, we see a massive electron density increase. So that is one observation. So we see like it's all the way from 10 to the power 5, go up to 10 to the power 18 or around 17 or 18. That's a massive increase. And then the fifth point is what do we have in the final plasma? Similarly, for the neutrals plot,
5 more minutes. 5 more minutes.
Yeah, I'm almost at the end. So, and finally, at the neutral density, neutral plots, you can see at 20 EV and 25 EV. At 25 EV, we are reaching the peak densities for 90 kilometer altitude. And similarly, you see the peak values reached for ions at that value. So the top key points, the first point, which I discussed already, why we are not showing 100 and 110 kilometer altitude results. Then I explained, so the reason why, if for the second and third point, why we have high O2 plus and O2 minus density in 1, 3, and 5 EV energies because of the reactions. So it's also obtained from that reaction thing that the code that I wrote, and these are the reactions that are causing it to be high in the density. And then the observation which we saw, which was like 15 to 20 EV, we have high electron density because it dominates in that region, in that energy region for 90 kilometer altitude. And the final plasma, similarly, like 80 kilometer, consists of E, N plus, and O plus. ABBT performance calculations. So now what we have done is, by varying the electron energy, keeping like different by performing like multiple, like hundreds of simulations to find the best optimum energy, like low and high energy for 80 and 90 kilometer altitude, we have plotted a graph of charge density versus the time ratios of extraction. So if you remember, time ratio tau1 was for negative ion extraction, and for tau2 was positive ion extraction. From these time ratios, from this graph, we can find out for 80 kilometer, this is the time ratio, something around between 10 to the power 5 and 6, and something for 90 kilometer, it's around 10 to the power 6. So based on this, we can design our like the extraction time for the electrodes in order to achieve neutralization. Why neutralization? Because here the charge densities cancel out, so they are intersecting at each other, so they're canceling out. And similarly over here. So the graph on the right, you can see, is a graph of force with respect to the different geometries of the thruster, which is the channel width and the discharge voltage. So we see like the thrust is always greater than drag in our experiment, in our calculations. So in this slide, you can see we have calculated a thrust, let's say for 300 volts discharge voltage, typically for like hall thrusters around that voltage. And we see like the thrust is right just above the drag, and which is sufficient. So our objective is to get like thrust equal to drag, something around that, in order to maintain or like the orbit. And then you see the power is very high and drag is very high. So the reason is like, for especially for drag, we have assumed like we are calculating maximum possible drag, whereas in reality only the lateral surfaces will be experiencing the major drag. So we can reduce the drag even further by performing like future simulations, like DSMC simulations, and the power will automatically reduce. Why? Because here we are achieving 100% ionization, whereas if you go to a higher altitude, we don't need this much amount of thrust, which means we can have lower ionization rate, and even with like 10 to the power minus 3 or minus 4 ionization rate, ionization degree, we can have thrust such that we can counter drag. So that is what I'm currently working on. And it's not in this slide, but just to give a spoiler, something around 100 to 106 altitude is the best altitude for our case to operate like air breathing plasma thruster in a power around 15 kilowatt NS. So I already talked about this. And transferring power, you can transfer power using laser beam. So that's a concept which has been explained in these references. Future work. So currently I'm working on characterizing. So I built an electron source and I'm currently characterizing it. And also already we have come up with the design. So we are fabricating it, and we will analyze the design using different plasma diagnostics and do thrust indirect and direct measurements. Then we want to basically compare the ionization results with experimental approach. We want to find out ways to increase the ionization degree in 100 to 110 kilometer altitude. And obviously, we also want to like find out different ways to reduce any extra corrosion that can happen. And we want to do a complete power analysis. So we have estimated power based on ion current, whereas it's very difficult to calculate electron current in Hall thrusters because of anomalous transport of electrons in Hall thrusters. So we want to do that analysis in future as well, like an in-depth analysis. So yeah, that's pretty much it. And these are the references. Thank you. If you have any questions.
Virtual applause. Thank you, Anmol, so much. We have a question by Orega. Orega.
Hi, thank you so much for the presentation. It was really great. I have a couple of questions. So you mentioned that you guys want to remove having a neutralizer or a cathode, but if you were to consider one, what would be the best option for this application? What kind of cathode?
So the electron source that I'm also building right now can also be used as a vacuum arc thruster, vacuum arc kind of a cathode, which does not require external propellant tank. And also, like, if I want to emphasize more about, that's a great question. The reason why we don't want neutralizer is because it kind of breaks the main thesis of our idea, like the main argument of our idea, which is like, if we have a neutralizer, we need a separate xenon tank or separate tank for that. That will again add the weight. So we want to have a thruster which does not have any kind of external tank or something, and everything is obtained from the nature. Everything is obtained from the residual air.
Okay. There's the cathode I heard of. Not that I'm suggesting or anything. I was just curious. There's the cathodes, field emission cathodes. Yeah. Those don't need the propellant and stuff, things like that. So I was just curious to see what was the reasoning. Another question is, do you collect the propellant on the way up, or do you collect it when you're in orbit?
So we are collecting when we are in orbit.
Okay.
So as it's going, so it's like having a steady orbit, pretty much like how our conventional airplanes work. So obviously we'll take the engine to a very high altitude, and once it reaches an orbital speed, we can keep this up. We want to just make sure that the thrust is equal to drag in order to just counteract the drag in that region and maintain that orbit as much as possible by continuously. So it's a dynamic system, something I would say we have proposed something like what Dr. Kiter did is a scramjet type of Hall thruster.
Yeah, now I'm just thinking and connecting it to the previous presentation on if there's some instability in the atmosphere, how's that going to affect?
It's gonna all answer when we test it in space. Cool. But definitely, that's a great question.
Yeah, it will affect it a lot, I think. Yes.
And we will primarily orbit, we will primarily be targeting the sun synchronous orbit to make sure we have power always. But definitely, yeah, we can collaborate on that. Definitely do research for sure.
That's interesting. I just didn't know what's happening at the 100-kilometer, if there is an instability or if it's going to be effective. So that's cool that GitLab could also have feedback on this. Last question is there an effect on the thrust when you're inverting polarity?
So for the positive ions, so what we observed was that we have a very less potential drop. So positive ions will not be accelerated that much. So it's majorly the negative ions when we extract them, they are the one actually causing the maximum amount of thrust. So in the thrust, we have if you see the equation here, we have averaged the thrust based on the time ratios here. Oh, sorry, I didn't write it, but we have averaged it based on the time ratio. I didn't write that the equation by mistake, but positive ion measure, it's going to be majorly negative ions, and that's good because oxygen has higher atomic mass than nitrogen, so the ions also will be heavy, so we should have higher, and thrust is directly proportional to mass flow rate, so that should be a good way.
Okay, thank you. Yeah, that's all for me. Thanks again.
Thanks for the questions. Thank you.
Thank you. Great question, Larega. Are there any other questions from participants or from attendees?
Hey, Mo, this is Brian Beeler. I kind of just wanted to piggyback off that statement that was just made. So based off the response that you gave, I think the major value added for your case that validates that investigation of the instabilities in the ionosphere is that the trade-off between bringing that fuel from Earth, I mean, that's the main thing, right, is that it's super expensive to bring that fuel into the orbit. So whatever challenges you are facing, based off like the status of the field or the technology, it's better to face those challenges and those instabilities than to move that fuel from Earth, because that's a huge cost driver that makes a lot of the mission.
Like fuel, which fuel?
I was talking in reference to the fuel that you're collecting in the ionosphere.
Oh, okay. Yeah, we are not carrying any like propellant tank or something. It's just everything is collected from the very lowest orbit.
Right, I think that's right. Like that's what you're gaining off of it, right, Brian? Is that what you're saying? Sorry. Hello?
Say that one more time, you cut out.
I'm sorry. That I think your point was exactly that you're gaining not having the fuel. So then the counterpoint is your instabilities versus your gain from not taking the fuel. Is that correct?
Yeah, just analyzing the trade space.
Or maybe I misunderstood your
under,
question.
From my understanding from the question, it was under question as to like the challenges that were faced as far as like inconsistencies, as far as generating that energy. But I was just clarifying that whatever inconsistencies or challenge you're facing, is much better to face those challenges and address those than to try to generate fuel on Earth and then bring it up to that level. So that's what we're facing in the space industry, is like how can we in situ utilization, basically.
Mm-hmm.
Just an observation or addition to the conversation.
Awesome. Thanks, Ryan. Any other points, Anmol, or anything anybody else wanna add?
Yeah, feel free to ask, even if you guys even have any biology related questions too. My friend is there, I think.
He brought Vic in. That's right.
Because yeah, feel free to
I'm
ask
still
him.
here.
He's the guy from NIH. Yeah.
Actually, I will ask Anmol actually one more question. And it's the same thing I asked Gilda, which is, I see some intersections here, definitely with the diagnostics course, definitely some with the computational. What do you see as good intersections between this and what you're seeing or expect to be seeing this?
Like from the courses, like intersecting with my research.
Yes.
Like the questions like that I was raising like during the lectures were pretty like prominently like focusing towards that. The first intersection was, how do we measure negative ion density? Because we want to see like the neutralization is happening, so we want to measure, like we want to make sure that we can measure. We have ways to measure or like see the emission of like negative ions. And negative ions are definitely very tricky in nature. So that is one thing, like the optical emission spectroscopy, and especially when Dr. Semeni talked about, and I just received an email from him too, I'll talk with him about it, when he talked about absorption spectroscopy. We use the optical emission spectroscopy in lab and like microwave scattering in Raman, but like absorption, and he was talking about like we can also see the like lower densities, and I was like interested in that, and I like asked the question about it. That is one thing I was saying, like definitely interacted. Another definitely most important thing is, which I feel like is one of my weaknesses, the simulation modeling in Hall thrusters, which is definitely like still very much in undergoing research. So I was the experience of like learning about the PIC coding today, like the underlying like physics involved in that and all that was very, very, very interesting. Like that was like something, another that thing that kind of crossed with my research. And apart from that, like I would say, yeah, majorly it was the computational physics, and definitely like stellarator talks were great, but majorly the computational physics and the idea of like plasma diagnostics and probes as well. Like that's why I asked about the B dot probe yesterday. I've never like used it before, but I thought like it would be awesome, interesting to see like you know, how much the electrons are getting magnetized or like it's like happening in the plasma. So, and I'm currently using probes, so the like Langmuir probes as well as the cup as well as Langmuir probes. So I was asking, that's why I was asking him how do we calculate electron temperature from the graph, because I actually had to do that this week. So yeah, it's
well, I'm glad there's that good intersection. Excellent.
Definitely.
All right, are there any more questions? If not, let's give Anmol another round of applause, virtual applause, if that's the case. And I believe we'll finish. Actually, I do have a bit of an announcement tomorrow. If you look at the schedule, let me see. Let me make sure I did upload that. Yes. So tomorrow is going to be a little bit different. We're going to actually start at 11:15 with a tutorial on SimSoft installation that Elizabeth Paul is going to be leading, and that's going to be important for Stellarator 4, the lecture that's going to be on Friday, because there's going to be some hands-on computational work there. So please be sure to stop by at 11:15 to do that, and then we'll go straight into the undergraduate poster session, and I will share with all of you via email the list, the spreadsheet where you could see all of the presentations. Actually, I believe you might already have them, but no, maybe you don't. So we'll be sure you have them, and we can spend the first few hours going through the posters. Anything else? Any other questions about what we expect in the next few days? Okay. All right. Oh yes. Arega, do you have a question?
Yes, just a quick question about the GSS poster sessions on Thursday. Yeah. Is there a time assigned for each presenter?
No, you will be. Staffing your Zoom session will be like standing in front of your poster. So you open it up, and throughout the whole window, you should just have it open. And there will be times that it's going to be a little bit quiet. Then I would recommend to jump like to other posters. That's what we tell the interns here, to just stay in front of your poster, which is just have your Zoom session open. And then if you've got some time, you can use another device to jump to another one. Didi, you had your hand up?
You just said what I was going to say.
Oh,
use your phone or your iPad or a different device to go into a different Zoom.
Yeah, that's the best way of doing it, so that if somebody jumps into your presentation, you can jump back into it. But does that make sense, Arega?
Yes, but how do we? So let's say it's 2 p.m. and I'm just gonna start presenting, and if anyone shows up, they just
no. So it's like a poster presentation. So you open up the Zoom, and most of the time, or hopefully not most of the time, but a lot of the time, you're going to be alone in your own Zoom session. And then if somebody joins in, then you start a conversation. You share your screen with the poster. They will have access to the poster, and you can have a conversation about the poster with them on the Zoom.
Okay.
Does that make sense?
Yes.
Does that make sense?
Yes, it's all clear now. Thank you.
Okay. Okay. I didn't want to confuse it. Definitely don't just start talking to an empty room.
Yeah, that was a little confusing part, but yeah, thank you so much.
Okay, exactly. And that's what I'm saying, that if nobody's showing up, or if you have a window, just like in a real poster session, that when you have some time that nobody's showing up, you can just walk off a little bit and take a look at your neighbor's posters. I would say you can do that with another device. That would work. And I saw some innovative stuff today. Somebody like shared a screen saying, "I will be back in 5 minutes," while they were in another Zoom. So just play it a little bit by ear, but be sure that you're there a lot of the time so that people can ask questions.
Arturo, was
And,
that Matthew
Didi,
Farr?
No, I saw it with Izzy. I didn't see Matthew.
Ah, okay, because I gave Matthew that idea.
Good. And have you made Didi? Have you made a Google Doc for each one of the GSSers for the questions?
I made one
notes?
this morning for the 10 people who had their stuff up. I haven't been able to go back in and do it, but by tomorrow morning it'll be done. For whoever else has
Right.
their
So
stuff
we did something with the interns, which is in the spreadsheet have a Google Doc for people to come in, and if you're not there or if people are watching your presentation at a different time, they can ask questions and put them there, and then you can get back to them. So that's another way of interacting with people. Does that make sense, Arega? I don't know. That was another. Anyway, okay.
Yes, yeah. Thank you.
Okay. Pavitra, you have a question?
Yes, quick question. So this particular poster presentation that you were discussing, is it tomorrow or is it on Thursday?
No, no. The GSS presentation is on Thursday. That's where y'all are presenting. But the undergraduate poster presentation is tomorrow. And that's where we're dedicating some time of this summer school to just going to the poster session. Yeah?
Okay. So we are just supposed to visit people's poster sessions during this time tomorrow?
Yeah, look at during the window in the schedule that says undergrad poster session.
Okay. Okay. Thank you. Thank you for the clarification.
Does that make sense?
Yes, it does. It does. I just want to make sure if we were going on tomorrow or on Thursday. I just want to clarify that.
No. It's y'all are on Thursday.
Okay.
Yes, from 2 to 5:30.
Okay.
5.
Okay. Thank you.
Okay. All right. Any other questions?
Yes, I have a question.
Yes, Gilda, go ahead.
Yeah. The poster session is just for people from the school, or is it open to people that's not?
No, it's open. It's open. If you want to invite anybody, feel free to do so. And we have told PPPL. So PPPL staff and students, and also the SULI students are invited to come in. So we've told a bunch of people.
Okay, great.
Yes. Please feel welcome to share it with some academic circles that you trust. There's a lot of Zoom session there, so just make sure you share with people that are trustworthy. But please share it. Absolutely share it. Yeah.
We're going to have coffee breaks.
Yeah, go. Definitely. If you can walk with your computer to get your coffee, do it. No, but absolutely. Have breaks. Of course, take your break. All right. Any other questions before we head out? All right. Well, we'll see you tomorrow at 10:15 Eastern, whatever time that is for you. And thanks again, Anmol and Gilda, for presenting today. I will send out the email to the other folks that I've talked to about presenting, just to make sure that everything's all right. And please, of course, send us an email if you have any other questions. And see you tomorrow.
All right. Bye. See you.
Bye.
All right.
Bye.
See you. Take care, bro.